Thanks for the introduction. I'm Tomoko Hashida from Waseda University. Our work is titled Fairy in Pixel. I'm presenting this research on behalf of Jin Himeno in collaboration with Tomohiro Yokota. First of all, what is Fairy in Pixel? Fairy in Pixel is a transparent real-world pixelization filter system that enables real-world objects to be pixelized gradually and selectively. In this presentation, I will show the motivation for this study with the design, implementation, and interactive application of Fairy in Pixel. Now I will explain the motivation of this study. As you might know, there are many interactive surface technologies that project and superimpose information in the real world. This is a type of technology that attracts people's attention by adding information. In fact, however, too much information is not always a good thing, you know. Rather, in everyday life, we're curious about objects behind frosted glass or blurring filters as shown in these figures. In other words, we may be naturally attracted to somewhat subtracted information. Furthermore, we are often interested in local blurring techniques such as pixelization rather than global blurring. Pixelization is frequently used in information technology and makes still image or moving pictures more difficult to see by filling the full area of an image with a representative value of a certain area. Paradoxically, people are often interested in pixelized image because they suggested that important information is hidden there. So, in this research, we set our goal to explore novel techniques for blurring real-world objects with a physical filter that changes their appearance and naturally induce a line of sight. As a type of filter and its effect that meets our objective, we focus on pixelization filter. Additionally, to make it easier to people to notice real-world objects with a pixelization effect, we believe that it is important to apply the effect selectively and gradually, rather than statically and immediately. So we propose a selective and gradual real-world pixelization filter. Next, I'd like to briefly introduce related research before talking about the Fairy in Pixel. As an example of blurring techniques for real-world objects, Pixel shows a blurred image on the opposite side to the light source, but the effect is not selective or switchable. Blur mirror blurs reflected images by means of vibrating mirrors. It uses a mirror to blur objects in the foreground. Fairy in Pixel, on the other hand, blurs what is behind the filter. SIGCHI locally controls the light transmission and shielding by using a modular array of an ultra-high liquid crystal seed. It aims to selectively hide or show real-world objects or information behind the filter. In contrast, we want to change the appearance of real-world objects behind the filter and naturally induce a line of sight. For this purpose, we implement a pixelization filter that blurs the object discretely or gradually. Information technology mainly uses pixelization to obscure information. However, there are other studies that use pixelization for unique use or effects. Hatters have utilized pixelization for inducing a line of sight without it being noticed. By blurring the area that is not intended to focus on, the area that is intended to be line of sight became more visible, and the viewer unconsciously guides the line of sight to the area with a strong edge. Hybrid image makes it possible to present different information when viewing something from afar or viewing it from nearby by overlaying two pieces of information with different spatial frequency bands. In our research, we pixelize real-world objects with a physical filter. Additionally, we want to explore similar effects in the real world, such as inducing a line of sight and switching viewpoints. Now we will move on to the design of Fairy in Pixel. Feeding pixel is aimed to pixelize real object gradually and selectively. We set our requirement as necessary condition for the mechanism to work. For real-world pixelization, it should be transparent and able to be superimposed an object in the real world. Moreover, it has the effect of filling the full area with a representative value of a certain area. For selective and gradual pixelization, the effect of pixelization can be turned on and off at any time. Additionally, the effect of pixelization occurs slowly. In order to develop a mechanism that matches above requirements, we focus on the design incorporating optical phenomena. First, we utilize the enlargement effect of the lens as a pixelized method. Through enlarging the center of the area by using a lens, we can create the effect of filling the full with a representative value of a certain region. By arranging numerous small lenses made of transparent resin and combining the magnifying effect of each one, we can make clear image as shown in figure on the left, appears pixelized as shown in figure on the right. We can easily create a lens array by using 3D printing of transparent resin. Second, to make the pixelization selective, we exploit the optical phenomena that light doesn't reflect at the boundary between material with the same reflective index. As shown in the figure on the right, by filling in the irregularities of the lens with a liquid that has the same reflective index as that of the transparent resin, no reflection occurs at the boundary of the lens, and the enlarging effect doesn't occur. As shown in the figure on the left, the enlarging effect of the lens can be activated again by releasing the filled liquid. Repeating this filling and the discharging makes it possible to apply the pixelization effect selectively. Additionally, by using liquid to control the switching of effect, inevitably pixelization on and off occurs slowly. Therefore, as our proposed method, first, we create a transparent resin casing featuring a lens array on part of this surface by using 3D printing. Second, we control the filling and the releasing of a transparent liquid having the same reflective index as the transparent resin. I will now explain our implementation based on these approaches. This figure shows the system configuration of filling pixel. It consists of a transparent pixelization filter, a wooden frame, a tube, a solenoid bulb, a small underwater pump, a photoreflector, and a microcomputer. In the following section, we divide the explanation of filling pixel hardware design into two parts: the transparent pixelization filter system and the control mechanism of transparent liquid. The transparent pixelization filter is composed of a lens array layer, a frame, and a lid. The lens array layer and the frame are modeled with a 3D printer, and the lid is adhered from the bulb. A transparent material having a reflective index of 1.49 is used as a resin material for the 3D filter. An acrylic plate is used as a lid material. The size of the filter is 480 mm by 320 mm. The frame height is 50 mm. A hole for the tube connection is drilled into the lower part of the filter. The shape of the lens array part in the designed filter is shown in these figures. It is a planar convex lens. In this implementation, the pitch between the lenses is set to 9 mm, and this pixelization filter is placed about 100 mm away from the object in the real world. Now, we chose this value after visually examining the pitches with which the painting used in our application example could be pixelized by making a moderate blurring adjustment. The control mechanism of transparent liquid composed of a tube. a small underwater pump, a photoreflector, and a microcomputer. Liquid paraffin having the same reflective index of 1.48 is used as a transparent liquid material. The tube connects the bottom of the pixelization filter with a solenoid valve and the underwater pump, which are controlled by the microcomputer. To facilitate interaction with the viewer, we designed the control mechanism so that when someone stares at the pixelized object, the detailed part becomes visible. When the viewer approaches the filter and looks into the frame, it receives input from the photoreflector sensor and stirs to fill the casing with liquid. The following shows the behavior of the implemented system. First, as shown in this video, the filter, a form of expression similar to an analog mosaic, was realized. Second, by combining the transparent pixelization filter and the control mechanism of transparent liquid, gradual and switchable pixelization was realized. As shown in the movie, when the artificial flowers are placed on the other side of the filter, they appear pixelized when the transparent liquid is released, and then appear clear when the case is filled with the liquid. It takes 60 seconds to fill the case with paraffin and 90 seconds to empty it completely. We devised two applications for directly or indirectly applying the function of changing the appearance of objects in printed photos and paintings. As an application of directly applying the function of changing the appearance, we implemented an effect in which printed photo is made to look like an oil painting or a pointillism image. We used panels or photos and the painting printing on paper, which were installed 10 cm away from the filter, as is shown in this figure. This movie shows a photo known as Monet Pond blurred by pixelization to resemble an oil painting. It then shows the photo as the pixelization is gradually being removed. As an application of indirectly applying the function of changing the appearance, we implemented the effect of switching viewpoints. Specifically, we created an effect where painting embodying a different information in the micro and macro viewpoints can look like a different painting depending on whether it is pixelized or not. In this application, we used the panel print of the Earth by Archibald. This sketch depicts the figure of a man composed of multiple animals from a macro perspective. The viewer sees the figure of a man, and from the micro perspective, he or she is treated to the appearance of the animal composing the figure. Normally, when the observer changes the distance from the painting, switching between micro and macro viewpoints changes the viewer's perception of the painting. In contrast, when we use the proposed system to cut the detailed information by pixelization, the man's profile is all that is apparent even if the observer at the same position as is a micro view. Furthermore, when the filter is turned off, the animal that makes up the profile of the man can be seen at the same position. We performed an evaluation experiment using Fairing Pixel to gather qualitative feedback on its concept and viewer experience. We presented Fairing Pixel at Grayscale Exhibition, an art show held on February 10 in Tokyo. Over 200 people attended in order to obtain the feedback about the concept and the experience of Fairing Pixel. We watched the participants during the exhibition and invited them to comment on what they saw. We displayed the two applications described above, and we also announced visitors when they asked us to display their own faces, belongings, or something. The viewers who were originally interested in the pixelized image were surprised and amused when the pixelization filter was turned on and off, the panel gradually becomes clearer. This attracted the attention of more people who gathered around to see the system in action. There were many positive reactions and many helpful comments such as, "This system reminded me that there is a moment that looks more beautiful than usual when I looked at the real world by removing my glasses." Taking into consideration of the effect of novelty, it is suggested from the user's behavior and the remarks that inherent effect of changing real-world objects and naturally inducing a line of sight were to some extent achieved in proposed system. We implemented the first prototype system, but there are still various limitations of both its pixelized and non-pixelated state. First, since the focal length of the lens array is fixed to the optimal pixelization effect can only be achieved when the object surface is at a certain distance to the lens layer, and when the object is flat. Second, there is a problem concerning the clearness of the image when the pixelation is off. Third, this time we emphasize the gradual nature of pixelization, which resulted in a longer latency compared to electronic approaches such as using liquid crystal. Finally, the implementation filter had a fixed size. I will now move on to the summary. Pixel is a transparent real-world pixelization filter system that enables gradual and selective object pixelization. Judging from users' behavior and remarks, it is suggested that the intended effects to changing the object is achieved. Our future work will address changing the degree of blurring dynamically depending on the real-world object, increasing the clearness of the image, exploring the various gradual effects, and making filters in various sizes. Thank you.
Thank you. Questions?
Yeah. I'm Untitled, Interactive Media Lab Dresden. Thanks a lot for this interesting work and talk. And I was wondering a little bit about the size and the shape of the lenses. So you showed this rather small hexagonal shape. And on one hand, of course, it limits like the art effect you can produce, like in your exhibition, because it always looks very similar. On the other hand, it does not really blur a person or something, because you can still recognize the object behind. So what is your take on how can you change the size or even the form of these lenses? Is it easy to produce a different size or shape of the lenses?
Thank you for the questions. As you know, changing the size is not impossible by using the more nice 3D printing system. But if I want to dynamically change the shape or distance, depending on the real object's shape and the size, we should change some system. For example, we should laminate some these filters, or we should change the pitches of the filters or something like that. So now I fixed this size depending on our applications.
And how did you determine this size? So did you experiment with various sizes?
Yes.
I don't mean I mean a static size. So did you try a bigger one or a smaller one as well?
Oh, I tried a smaller one, because you know the size of a filter is depending on the size of the 3D printer can print. Yeah.
Any other questions? So maybe while the next speaker is getting ready, I have a question regarding the difference from prior work. So I was at AVI 2012 when Junrei Kimoto presented his work, Squama, and I want to ask you maybe to spell out what the main differences between his system, which is almost real time. I don't know if you saw the video where there's a user behind this screen, and the pixels can follow the user to block him. Is your system, is the resolution maybe finer? Is it the cost? Or what is the main difference from that work?
In the schema?
Yeah.
Yeah, it's a good question. You know, the schema change the transparency and become white to clear. So, but my filter use a pixelization. So I think the effect the effect is a little bit different from the schema to my system. Is it okay?
Yeah?
Yeah.
Okay. So thanks very much again, Tomoko.